welcome to my talk. Safety first, understanding how to develop safety critical software. This is me. I am one of the co-organizers for the Munich C++ user group. We are one of the largest user groups in the world for C++. We're always looking for a new speaker, particularly if you haven't given a talk before and just want to try it out, please reach out to us. We're always happy to welcome new faces. I've been working in the automotive industry on safety critical software for a number of years now, which is why I decided to give this talk. I'm also a member of the MISRA C++ working group, so if you ever had to work with those guidelines, then I'm partially to blame. And I'm also a member of the ISO C++ standards committee. I'm currently working as a runtime engineer for Woven by Toyota. You might have seen the keynote from my colleague JF Bastian yesterday. So what is the motivation for this talk? So I actually submitted this talk for the first time to this conference in 2020. And it was accepted, but then the pandemic happened, so I wasn't able to give it. And then I kind of lost interest in it and gave a different talk last year. But then, since the conversation about safety started picking up so much again, I decided to resubmit it again. But since this year we had so many talks on safety, I decided to shift the focus a little bit and use it mainly to give you sort of an inside perspective of what it means to develop software in a regulated field. So we have heard a couple of times this week, and we've seen it on the slides of the keynote yesterday, that there's this distinction between the software craftsman and the software engineer. So if you were socialized in a similar manner than I was, then you probably have come across these books at one point or another. And I actually really like these books, and I really like the analogy, especially the cover of the software craftsman, where it's you want to build this really sophisticated, beautiful violin, and it requires a lot of skills to do that, but in the end it's something that you can really be proud of. So I think this is a very, very good mindset to approach programming, but it focuses mostly on programming skills, right? That is what they try to sharpen there, right? To make sure that you master your tools and that you're able to make the most of them. Engineering is worried about a different thing, right? So of course, mastery of your tools is an important enabler for being able to do good engineering. But engineering is also a lot about responsibility, about methodology, and in the end also about accountability. And that becomes particularly important when you're facing regulation, because then this accountability, that's a very real thing, right? If your software misbehaves and something bad happens as a result of this, not only your company, but potentially you yourself as the engineer that wrote this software might be accountable. So as I said, today I want to give an impression what that's like working in such an environment and how it changes how we approach software. So fair warning up front, this is going to be quite a boring talk, right? Probably the most boring slides that I ever did. There's no code in there. There's very little about C++. There's a lot about processes and boring regulatory stuff. So please feel free to ask questions and participate. And if you want to know more about something, raise your hand. If you think that something is super boring and I should move on, then feel free to signal me, right? So this is the outline for today. We will very briefly, again, as we've done a couple of times this week, talk about what is safety. Then we will have a look at what are the regulations around functional safety, which is a very important kind of safety for many regulated fields. And then we will spend the majority of the talk taking a tour of an ISO standard for software development in such an environment. And of course, we will also discuss what it means to be using C++ in such an environment and what the implications are. So what is safety? We've seen this quote before in Sean's talk, if you attended it earlier this week. It's a definition given by Leslie Lamport that is very popular among computer scientists who work on software verification. So they define safety as something bad does not happen, right? So this is not a super precise definition, but I really like it. Like, it's catchy, and you can sort of get what it's aiming at. So there's some examples for this. Partial correctness, that's an important property in theoretical computer science. Your program does not produce the wrong answer, right? That's a safety property. Mutual exclusion is a safety property, right? Two processes will not be able to enter the critical section at the same time. Deadlock freedom is an example, right? The program does not deadlock. So this is the computer science definition, and if you've been looking into program verification, then you've probably seen this before. It's very useful in this field. But what we're going to talk about today is a very specific kind of safety, and that is functional safety. And they have a slightly different definition. So I'm going to base most of this talk on the ISO 26262 standard, which is functional safety for road vehicles. And they have a pretty extensive, the entire standard is comprised of 12 parts, and the entirety of the first part is just defining vocabulary. And they actually, it's pretty insightful to read through this, because it's very precise definitions, and they really get you into the mindset of what it means to think about this and discuss it really in precise terms. So they define harm as physical injury or damage to the health of persons. And this is a very specific definition to these particular fields, right? Like, for other fields, you could imagine other wider definitions of harm, right? So, for example, this does not take into account financial damage, which might be very important in other fields. But even when we're just talking about the well-being of humans, just think what could be a definition of harm for a cryptocurrency, or for a social media platform like Instagram, or for a video game with in-game purchases, right? These are all technologies where people have been raising concerns about the potential of harm for the environment or for human beings. So going on from this definition, the ISO defines the term risk, which is the probability of the occurrence of harm weighted by the severity. So we also heard this before in other talks this week. There's always these two factors, right? It's not enough for a source of harm to be very severe. If it's astronomically unlikely that it will ever happen, then the overall risk is quite low, right? So both factors have to be taken into account. An unreasonable risk is a risk that is unacceptable according to societal moral concepts. And this is where it gets a bit fuzzy. So usually there's some amount of consensus within the industry what this means. But of course, there is some wiggle room here, right? So in the end, this is part of the good judgment of the engineer, what is considered acceptable here. And now safety is simply the absence of unreasonable risk, right? If we define unreasonable risk, we want to avoid that. And that is the whole goal of these 1,000 pages standard to achieve this. So functional safety, this term, what does that actually mean? So in this particular case, and actually most functional safety standards are considered with electronic systems. And as we all know, these systems can fail for various reasons. In particular, these standards distinguish two different kinds of failures. We have the systematic faults, which basically means it's a deterministic failure that occurs every time once a certain set of conditions is met. And these are typically design failures, right? So design or specification failure, right? Either I did not take into account some situation during the design, and therefore I fail in certain circumstances, or simply like my design is faulty, right? I have a bug, for example, right? So and actually like software bugs, all of software failures fall into this first category. And the second category is random failures, which is failures that are unpredictable, but they follow like some kind of probabilistic distribution. And this is a hardware topic. So hardware people are really good at this. If you get automotive grade hardware and you look at the data sheet, you have like all kinds of probabilities for how they could fail and what the expected conditions are. So functional safety wants to reduce the risk, as we've seen before, resulting from such faults in the electronic systems. So a fault in the ISO standard is just an abnormal condition that can cause an item to fail. And like an item, you can think of it as like in the software world, it could be a program, right? Or like a process that is running on the vehicle, right? So something goes wrong, like either the hardware has some kind of defect, or you have a bug in your program, and now it no longer works as expected. And they distinguish different kinds of failures there, different kinds of faults there. The order of events, how it's defined by the standard, is you have the fault, which is basically the condition that causes the program to fail, and that can lead to a failure, which is then actually like the intended behavior that the program was trying to achieve is no longer working as intended. And then a subset of these failures will be hazards, which means like the program is no longer working, and now as a consequence of this, there's a source of harm. So like a human could get hurt. So the most obvious way to ensure safety in these fields is to prevent the faults, right? But that is not the only way. In particular, like there's some faults which are just not preventable. And the ISO very much embraces this notion, right? You won't write a bug-free program, right? It's not realistic to just say, I won't have any software faults because my software is going to be perfect. And for hardware, that's even more obvious, right? Like there can always be like some condition under which the hardware no longer works. And functional safety in large parts is about embracing that fact that faults will eventually happen, but we still want to make sure that as a result of that, we don't cause any harm. So that is the mindset that they are starting from. To really understand what functional safety is about, it's helpful to actually see like what is not functional safety, what is outside of this. So one example is like just quality management. This is just like general like software quality. Make sure that the product that you ship is like not garbage. And the corresponding standard here is the ISO 9000 family. So typically you get an ISO 9001 certification for this. That basically says like, yeah, you know what you're doing, right? Like you have an essential quality management process. You're able to identify problems. You're able to react to problems. And like people in your company generally know what they're doing, right? And it's not total chaos. That's the baseline in very simple terms that ISO 9001 sets. So quick show of hands, like who here actually participated in an ISO 9001 audit ever? No one. So you've come to the right talk, yeah?
Well,
yeah.
so, there's other software specific standards,
Right.
right?
Yeah.
That,
Yeah.
It's the other one is it's escaping my brain right
Yeah.
now.
Yeah.
But definitely participated in those.
Yeah.
Like the level 1 to 5.
Right. Yeah. Yeah.
Yeah. So I don't know. Does anybody, if you get the that certification, does that sort of automatically give you 9001?
I don't think so. I don't think so. Because like certification companies like to charge differently for each number, right?
Yeah. So there's a business here too.
Yeah.
Right?
Exactly. Exactly. Yeah.
Okay.
But so it's important to take into account that like you need this baseline, right? You need to your company needs to be in a shape where it can produce like software that works, and everything that we're going to talk about with regards to safety comes on top of this, right?
So just going back to that point for a second, though, I mean, does this mean that, like in your guys' business, does it mean you basically have to have the 9001?
It depends a little bit on like the cultural context. Like in Europe and Asia, I think that there's a little bit more. It's deemed a little bit more important than in the US. Yeah, but in general, I would say you need something like this as the baseline. If you don't have that, then probably you're going to get into trouble at one point or another. Yeah. Another thing that we have in automotive is the safety of the intended functionality. And the difference here is that functional safety is really only concerned if something fails, right? Something is not working as expected. But you could also have sources of harm if everything is working as expected. So for example, there can be functional insufficiencies, right? Where it's just like you have a certain sensor and that sensor just doesn't work under all conditions, right? Like if it's snowing a lot, then just the sensor is no longer able to detect the environment. And then if there's a car in front of you, it might crash into this, right? And that might just be part of how the functionality works, and that's just a natural limit, right? You just don't use this functionality in a snowstorm because the sensor won't work reliably. A big factor here is incorrect handling by the user. This is also takes into account things like the user interface, right? Like if the functionality is presented in a way that it's easy to mishandle or easy to misunderstand by the user, this is a concern of safety of the intended functionality. And a big point that has come up lately is functional insufficiencies of artificial intelligence. So in particular, like if you look at the year here, like this standard was published in 2022, so it's very recent. And the very first edition of this was an ISO publicly available specification. Don't get confused by the name. That doesn't actually mean that it's publicly available. Nothing from ISO is. But it basically is a way to publish a little bit quicker than a full ISO standard. But that first edition was only published in 2019, so it's very recent. And the need for this being specified in a separate standard was very much triggered by the advent of these advanced driving assistance functionalities, because this is a huge topic. And this is also like one thing that is very typical for regulated industries. Like once you have regulations, you will probably accumulate more regulation over time. Another important aspect is, of course, security. There's also standards for this, and we also heard this earlier this week. So the difference between security and safety is mainly that in security you have an attacker, right? You have a malicious actor that is actively trying to break your system. And there's a large amount of overlap between the two, right? Because a lot of security problems can also turn into safety problems, right? If a hacker is able to compromise the system of the car and thereby disable a vital safety functionality, that's a safety problem. That is not always the case, right? So there are cases where you have a security concern but not a safety concern. So think, for example, about car thieves, right? That are able to to remove certain electronic parts and then resell them on the black market. For security reasons, you don't want that to happen, right? You want to have some kind of prevention, or also like people like circumventing like certain features that you don't want them to access. A big factor here is also data protection, right? Like you don't want data leaks of your system. So these are all security concerns, but not necessarily safety concerns, because there might not be a harm resulting from this. On the other side, you also have safety concerns that are not necessarily security concerns. For example, the protection against hardware failures. That is not typically something that security cares about. There's also a bunch of specific technologies that have their own standards. Oh yeah, Jeff, please.
So it seems like there's a hole here.
Mm-hmm.
And maybe there isn't. So, these definitions, whatever. So, your category there is cyber security. So
yes.
It's very focused on, how hacking this computer or set of computers or whatever. But we've definitely seen recently, again related to the sort of self-driving technologies, certain individuals that will apply actual physical techniques to confuse the systems of the car. So it's not really cybersecurity.
Yeah.
And the one I'm thinking of specifically is like, in a certain electric vehicle, they use the steering wheel, for example, to make sure that you're still paying attention. Well, if you put a weight on that steering wheel, it turns out, you can work around that system, and then you can sit in the back seat or whatever.
Yeah, that's true.
Your video for, likes on TikTok.
Right. So those concerns would probably fit into the safety of the intended functionality category. I think that's the But
so it's not really that second bullet. It's not incorrect. It's actually malicious, like the cybersecurity, and that's the thing that made me think it's kind of like a hole where, you need to anticipate that there will be users that will be malicious at the physical level.
Right. Okay. And it's actually a valid point, right? It's not always clear to which of these fields your problem actually belongs, right? So that's also like how this emergence of new standards comes along, right? That like something that becomes a prominent problem, and we're actually not sure where to address this, right? And now we actually figure out we need a new kind of standard for this.
Gotcha.
Timo.
So I have a question. So in JF's keynote, I think his central thesis was no functional safety without security.
Yes.
I'm curious what your opinion on this is, because it seems like that doesn't sound quite right. You can think about something that isn't secure, like for example, I don't know, an app that like transmits your password in plain text. But otherwise it doesn't have any UB or vulnerabilities or any way you can like hack the actual program. So it's like somebody just didn't implement the crypto to like transmit your password safely, but there isn't any way like to hack the program. So it seems like that's secure, but not like safe, but not secure. So I don't get how that's compatible.
No, that's true for like a very small subset of the safety properties, right? But the vast majority of properties, if you have a security problem, it can turn into a safety problem very quickly.
Okay, so it's not an absolute kind of rule. There are these like narrow cases.
Exactly. So there's these narrow edge cases, but if you look at a full system, it's very unlikely that you will have safety requirements where there's like where you have safety requirements where there's no concern for security, right? Like in a realistic real world system, if you have safety requirements, in the vast majority of cases, you also have security concerns. So for the specific technologies, there's like for example, there's special standards for like LiDAR sensors to ensure that they cannot cause eye damage, for example. There's special standards for AI and machine learning. These are very recent. And for example, like the ISO in particular says that it does not take into account cars that have been modified for drivers with disabilities, right? So it's like these are considered out of scope. So that's another field where like this stuff might not apply, and you might have to look into a different place. So with regards to functional safety, there's a whole family of standards for functional safety of electric and electronic systems, and they're all based on this ISO IEC 61508, which is the baseline for all the functional safety standards. And then we have further down there all kinds of like derived standards that all built on the groundwork that was laid by this standard at the top. So in particular, the one that I based this talk on, the one for road vehicles, which at this point I think is the most expansive of all these standards, the most detailed. That one emerged in the 2000s, and the reason why they needed to specify this was that there were just some concerns in road vehicles that were not addressed in this initial base standard. So in particular, when this initial standard was written, the main use case that they had in mind was production plants. And they put a heavy emphasis on external measures and separate protection systems, which in a road vehicle is typically not possible. In a road vehicle, typically you only have the vehicle and it needs to be able to handle all of the potential failures. Also, production plants are typically singular or low volume systems, whereas with cars, you have like 1 million of those cars right on the road. And that gives you a very different story, in particular when it comes to the risk analysis. So as a consequence of this, the complete hazard classification was basically changed in the road vehicle standard. Another important point about road vehicles is that the entire validation has to happen before production, right? Basically, before the first car leaves the real factory, you need to be done with the validation, which is not the case for the plant, right? With the plant, typically you build the whole thing and then you do the validation and then you start producing. And yeah, so there's different concerns like this, and similarly, like each of these standards takes into account like the specific requirements from that field. We also heard Bob Stiegel mention on Monday in the panel on safety the standard for medical devices, which is ISO IEC 62304. And I actually had a conversation with Bob last year at this conference where he told me about this standard and how much he liked, like how clear they expressed everything. So I also took a look at this, and that's actually very similar to this. Even though that is not technically a functional safety standard, the kinds of processes that they describe in there is very much comparable to what we have in these standards. So yeah, there's sort of a consensus how to do these kinds of things across the different industries. So how does this actually look like? Like what do those standards actually require us to do? So who here remembers the waterfall model? Yeah. So yeah, we don't like this that much anymore in software, right? Like in particular, if you think back to these books that I showed in the beginning, if you've been brought up in that mindset, you're probably aware of all the problems that this has. You have all of these different phases. Each phase follows the next, so you won't start the design until you're finished with all the requirements. And yeah, so this is a process that actually was adapted from civil engineering. It dates back to the 1950s. And it worked reasonably well there, but it has some problems that make it not really suitable for software. In particular, it requires this, what is often called like big upfront everything design, where like in the requirements phase, you basically have to develop a complete understanding of the system and put all of that down into the requirements before you then start working. Because of this, it's very difficult to make changes in later development phases. That's not really something that this model is good at handling. In practice, separating those phases clearly is just not practical. If you run short on time, guess what the first thing is that you're going to cut before going into production is the testing, right? So yeah, typically these projects tend to be poorly tested in the end. And also, like even if you do the testing, if you only detect errors in the testing, which is very likely, it's very hard to then adapt the design simply because like the whole model is not very good at handling change. So the functional safety standards don't want you to follow Waterfall, but they want you to follow something that looks very similar, and that is the V model. And the V model is something that was developed in the 1980s, so it's a lot more recent, and it mainly like took up momentum like during the 1980s. Like there was, for example, in Germany, there was a very successful adaptation of this for military projects, which worked so well that then in the early 90s they actually started to also require it for civil projects. And the difference here at first is like that for each of the phases that you went down in the waterfall, you now have on the right side a phase that actually verifies this step that you took while going down, right? So you have like different layers of testing and verification that validate the different phases of the design and the development. And like if you look at the names there, like if you've read a book on software testing, like this is all familiar, right? Like if you want to test a software system, you do all of this, right? You write unit tests, you write integration tests, you do system testing. So like this is obviously like a good way to ensure software quality, right? You have like these layers which are to some extent redundant, but they're able to like address all of these different concerns and make sure that like you didn't mess up on any of the different phases. What is a bit problematic is that you still have this this characteristic of the waterfall that like the phases follow each other, and that is something that is a disadvantage of this model. So you like especially since like Agile is such a big success story, not only in software but also in other fields. In modern development, you don't have this like strict separation where you say like one phase has to follow the other, right? So there is in typical project these days there is some kind of overlap, and you try to be more adaptive to change than you would be in the classical philosophy. But if you compare it to like really like the hardcore Agile methodology, this is very much not that, right? So there are some restrictions and there are some pain points arising from this that you need to be prepared to deal with, right? And this is simply the price that you have to pay for being able to get like this rigor that is required by the safety. Timo.
So we discussed this stuff, if you remember, at the CppCast episode, and we got some feedback afterwards. Mm-hmm. Where somebody said, well, V model and Waterfall are kind of orthogonal. Like the V model is all about having this decomposition into like different levels,
right?
And then having this like appropriate testing level that corresponds to the like, So this like back arrows and like the levels, right?
Yeah.
And so the claim of this person was that actually doesn't contradict Agile at all. And actually he pointed out that in medical, there is a standard called AAMI-TIR 45 called Guidance on the Use of Agile Practices in the Development of Medical Device Software, which describes how to practice Agile development in a way that the FDA will accept, which I assume is their regulatory body. So apparently there is a way to practice Agile and still be compatible with this.
Yeah.
I wonder if you heard anything about that.
So I wasn't aware of this particular standard. So the ISO basically has like a very short paragraph that says like you can adapt your process to be more agile, but they don't really tell you how, right? And in practice, there's always like some amount of struggle that like you try to do the design and you're missing some requirements, right? And then it's really hard to decide like how to continue from there, right? But it's I mean like with all development processes, right? Like the reality is always very different from the theory, right? And yeah, in reality, we'll always do some mixture of those. And yeah, I mean, there are clear benefits for being more agile. So yeah, I'm not surprised at all that like people wrote a document like this to enable that. Well,
Yeah, I was gonna say you can always have little agile cycles within this greater
yeah, right.
process.
Yeah. That's another possibility to have like smaller cycles within. Okay, so if you look at the overall 26262 development life cycles, it's like a V of V's. So you have like one big V cycle for the overall system development, and then inside of that you have like smaller V's for the individual hardware and software systems. That is sort of the structure of the overall thing. And for the remainder of this talk, what we're going to do is we're actually going to walk through these phases and look at what they look like. So we always start with a hazard analysis. This is the HARA that was on JF's slide yesterday, if you remember from the keynote. And this is done to identify the safety goals. Then from that, we develop like an overall functional safety concept for the vehicle. Which is, from that we then adapt a technical safety concept, which is the input into the actual development phases, like these smaller V's within the big one. And the ISO standard actually gives exact definitions for the different outputs and objectives at each phase. They still leave some room for interpretation, but they're precise enough that you have a pretty good idea of like what the expectations are. And then like each company still needs to think of like what the exact form is that in which they want to provide these outputs and what their processes are for ensuring it, but it gives a pretty good idea. A very important point here is that the ISO puts a big emphasis on traceability between the different phases. Because if you think about like systematic failures, design failures, one of the biggest sources that you can have for this is if you go like from one phase to the next, like from the requirements to the design phase, that there's like some kind of disconnect, right? Like you implement something that was not in the design like this, or you implement it in a different way than how the design intended it to be, and you just don't notice, right? This is a very common source for failures, and the standard acknowledges that and thereby has like these extensive verification layers, not only these horizontal layers that we saw in the diagram before, but also these vertical layers between the phases to verify that like the design actually follows what the requirements ask and the implementation actually implements what is specified in the design. And traceability is the key word here, right? So like how can I make sure that like I actually have a tracing from the requirement down to the implementation? Ezra.
Can you give an example of what, like during the hardware or software development phase, like what does the technical safety concept look like to them when they're in the development phase?
We will get to that.
Okay.
Yeah, we will look at each of the phases actually in greater detail. So yeah, let's actually start with the hazard analysis, since we heard a little bit about that already. So the goal of this is to identify basically all of the safety goals that our system is going to have. And we start out by just sitting down and just thinking about like what are all of the different hazardous events that could happen here. And the level at which people think about this here is at the level of vehicle functions. So if you look at the different hazards that they come up with, this is not super technical, right? So if you have a rough idea of like what a car is and what it does, you're able to follow this, right? So this is like, if the car is in this situation and the automatic steering does something weird, right? Then an accident could happen, right? And people could get hurt, right? So it's on this level. It's really, you don't need to understand what is going on inside the car, what the different systems are. It's really like, yeah, what is the vehicle function? And then for each hazard, we try to identify what is the severity of this. So like, how bad could someone get hurt, right? Because like, Some of these hazards, it's like, maybe you get like a scratch, or like your finger gets maybe squeezed a little. More severe hazards, like you could break a bone. Even more severe hazards, someone could get killed, right? So you have like all of these different categories, and the ISO precisely defines what they mean. And similarly, you also have like different probabilities, how likely this is to occur, and this is again precisely defined. And then the combination of the severity and the likelihood gives you the risk. And this is an exact mapping, right? Like once you've settled on like what the severity and the likelihood are, the risk, that is just like the standard just tells you that. You can just look that up in a table. And then there's the third factor that comes in, which is the controllability. So there is always the situation that like if the car misbehaves, but the driver is still able to control the behavior and like bring the car back to a safe state. And for some hazards that is possible, for others it's not. And if you have a high controllability, that might bring like the overall severity of the thing down. And then once you've taken the controllability into account, you arrive at what is called an ASIL level. And ASIL stands for Automotive Safety Integrity. And we have different integrity levels, so 4 different levels. The lowest one is A, and then the most critical one is D. And then we have a 5th one, ASIL QM, which basically means that the risk is within acceptable parameters, so we don't need specific safety requirements for this. If you have like this, so QM is short for quality management, so that means like if you meet your baseline for software quality, that is enough. You don't need to do anything in additional to meet your safety requirements. And then the outcome of this analysis is simply like a big list of safety goals and their associated ASIL levels. So just think like this is a giant Excel sheet which lists like all kinds of different scenarios where something could go wrong, and goes like through this whole thing and arrives at an ASIL classification in the end, right? Question?
How is like likelihood calculated? Because that seems pretty challenging to get.
Like that's true. So this is, so there are like certain parameters that are taken into account. Like for example, you can, you know like how, what the, like during the lifetime of a car, how big the percentage of that is that you're driving on the highway, for example, and that you're driving across a certain speed limit. And then if you have a hazard that only becomes severe if the car is traveling at a certain speed, then you can already say, okay, like, this is only going to, like, the car is only going to travel like 10% of its lifetime at this speed, so that impacts the severity. So it's calculations like this, right? Or like you have like, you need to be like in a really like specific environment, like this car needs to be there and the pedestrian needs to be there for the hazard to occur, and that is like not very likely or very likely. So it's conversations like this. But it's not an exact science, right? So this is again, yeah, like you need like some, good judgment from the engineer for this. Ezra.
And this is all done before the vehicle even reaches like production stage? This
Yes.
is all in the design / requirements phase?
Yes. So this is like the very first thing that you do, basically. Yeah.
So I realized that was an easy to understand example, but to kind of better understand what this looks like, if we think about like 10% of time in a car is spent at that speed, but say 50% of journeys involve traveling at that speed.
Yeah.
That's somewhat analogous to I've got a 99 percentile uptime, but I need them all to work across like 100 processes.
Yeah.
My effective failure rate is through the roof.
Yeah, exactly. Yeah, and that like this is not trivial, right? This requires like a lot of knowledge to do this correctly, and like automotive companies have experts that pretty much do just this, right? And they think about like all of these issues in great detail, and it's a fascinating topic. It's like a whole section of the standard that just talks about this. So if you want to know more, check this out. I think it's part 2 of the standard. So yeah, fascinating stuff, but not really related to software. So I don't want to spend too much time. So this ASIL level that falls out of this, what does this actually mean? What does this signify? And what this means is this is the degree of rigor that is required during the later development phases, right? So if you have a higher ASIL, that just means you need to spend more effort to make sure that this safety goal is met, because the impact of it is just
Yes,
potential.
I was going to ask on the last slide.
Oh yeah.
In these models, do they take into account things like the software failure? I mean, you're saying it doesn't have
Yeah.
much to do with software, but do they take software failure and that kind of thing?
At this level, not, because here we're just talking about vehicle functions,
Okay.
right? Only in the later phases we actually look at like who is responsible for this function and like what are the different systems that are involved here.
But I mean, obviously, if you have things like, anti-lock braking, just to pick one,
Yeah.
If the sensors or,
Yeah.
the software that runs those sensors has failed, then obviously that creates a risk, right?
Right. Yeah. Yeah.
Okay.
Although like, yeah. So, but you try to not get too much into the implementation here, right?
Okay.
It's to some extent you have to do this, right? Like because there are like some safety goals that like could result from like a particular configuration, like how the system is actually laid out. But like in general, I like to think that like on this level, this should not be relevant for most of the safety goals that you're thinking about here. But you can never completely exclude this, of course.
Yeah. Okay.
All right. Yeah, so the ASIL levels are like build a hierarchy. So if you fulfill a more strict level, then you automatically also fulfill the lower level, right? If you already comply to ASIL B, then you automatically also fulfill ASIL A. And the ASIL, as it falls out of the hazard analysis, is always associated to a specific safety goal. But as we move further down to the development, the ASIL is actually inherited down, right? So if I have a system that takes part in the implementation of like a specific functionality, and I have the safety goal associated to this functionality, then it inherits the ASIL. But as you move further down, sometimes like you lose sight of what the initial safety goal was, right? So in particular, if you're thinking about like you're writing a low-level software component that is, for example, handling like communication over the bus system in the car, right? Then there's a lot of functionalities that depend on this, right? So you will inherit the ASIL from like the most critical functionality that is making use of this, but you no longer have like really this connection of like these are all the individual safety goals that this came from, right? But still, it's important to know like where the ASIL comes from is the safety goal, right? You can't just pluck the ASIL out of thin air because like you feel like it. It's always associated here with the safety goal. All right, then let's take a quick look at the functional safety concept. So this is the highest level of design. And the way that this works is I look at the safety goals and now I derive from this a specific set of safety requirements, right? So this is like things that my system must do so that it meets the safety goals. And the safety requirements then inherit the ASIL from the safety goal. And of course, like a single requirement may be associated with multiple safety goals, right? And this is now actually getting a bit more technical already, right? Now you're taking into account like the individual systems, right? So you might say like something that the controller that is handling like the automatic brake control or the steering must not lose power, for example, right? Or something like this. So this is already now a design that takes into account like what the actual car is going to look like to some extent. And there's two outcomes from this. The one is the functional safety concept that describes like what you want to do, how you want to handle all of these safety requirements. And the other thing is the verification report. So that is sort of the other end of the V, where in the end, like you also have the proof, the evidence, as the ASIL likes to call it, that you're actually fulfilling what you specified in the concept in the beginning. So some of the strategies that we use in this functional safety concept to meet our safety goals. So the obvious one is just try to avoid the fault, right? If you can do that, then yeah, there will, without a fault, there won't be a hazard. But that's not always possible. So a big part here is also being able to detect the fault and control the impact, right? So if I notice that like a particular sensor is just sending out garbage data, then don't continue reacting on that data, right? Control the failure in some way. Another big point here is that we try to design the system to be fault tolerant. In particular, like if you know that if a sensor is critical for a safety goal, and you don't want that sensor to fail, then maybe just have 2 of those sensors, right? Or you can take that even further and like have an entire system be implemented either redundantly or even one step further, being implemented in diverse ways, right? So you have like the same functionality implemented by 2 different systems, which are actually like different designs, right? And they're completely independent from each other. This takes into account like, has to take into account like the timing. So when a fault occurs, you always need like a certain time until you are able to detect it. And then you have a certain time in which you need to react to it before you actually run into the hazard. Yeah, so we said like redundancy and diversity can be used here. Oh yeah, Robert.
So I always think you need an odd number of systems, right? So if you have 2 systems implementing the same logic in different ways and they disagree,
yeah,
which one's correct? But if you have 3 systems to implement the logic in different ways, now there's going to be hopefully there's going to be a majority opinion.
Yeah, right. Yeah. If you then have 3 different opinions, then it doesn't help. Yeah. So with 2 systems, if you just need to detect the fault, right, then 2 systems are enough, right? Because if they don't agree, then you know that one of the 2 is wrong. You don't know which one, but you then have an external mechanism that gets you back to a safe state, right? That is something that you can do. Yeah, but if you require the input from one of the 2 to get you back to the safe state, then yeah, you don't want to end up in this situation where you have a deadlock, they disagree, and you don't have a tiebreaker. Yeah. Another possibility here is to increase the controllability through driver warnings. And one thing that is very pervasive throughout these safety discussions is that you want to be able to define like this emergency fallback state, the safe state that like if there is a fault, like this is something that you can easily fall back on to avoid like creating a hazard. Like we heard in JF's talk and in Sean's talk, a car that doesn't move is safe, right? So if you can stop the car without causing other hazards by the stopping maneuver, right, that could be a safe state. All right. So the next step after this is the technical safety concept, and this is now the actual like the first actual development phase, where we really take a detailed look at like what will actually go into the car. So this will define like the concrete safety mechanisms that will get implemented, which need to fulfill the safety requirements that we defined in the previous stage. And this takes into account now concrete details of the implementation, right? Like what are the different controllers, how are they connected, what are my sensors, and all of this stuff. So here it starts to get really technical. An important point here is that the technical safety requirements now really need to be testable. We had a verification phase for the functional safety concept as well, but that could just mean like I do a review to make sure that actually like all of the stuff that all of the safety goals that fell out of the hazard analysis have been addressed right? But here, really, what you want to do is like really testing, as we know of software testing. Timo, you had a question?
No.
No. Okay. Right. So that now it's actually moving closer to actually building things. We want to describe the functionality of all of these mechanisms that we want to implement, along with like timing and tolerance properties. And the outcome of this technical safety concept is actually going to be the input then into like the actual development phase, like to the hardware engineer or to the software engineer that is then building that system. So up until this point, like you can actually do most of this without even having a software engineer in the room if you want, right? So this is, and like we already produced like a lot in terms of like work product and effort before we actually started the software development, right? And this is very typical for like these regulated environments, right? You have all of these layers where people look at the different concerns. There's a lot of work, a lot of stuff being produced before we actually, start building something. So let's now get a little bit more closer to like what we are all used to. Let's look at what the development lifecycle for software actually looks like. So similarly for software, we have a requirements phase, a design phase, an implementation phase, and then we have tests that verify the efforts for all of those phases. So our input is the technical safety concept, right? That are the requirements, like the technical safety concept assigned to our software. Like you need to make sure that like your system actually fulfills this requirement. It has been allocated to my system, and now my implementation actually needs to take this into account. And the requirement now needs to describe how my software implements the safety-related functionality. So this could mean I need to execute a nominal function. It could also mean I define like certain safe states or degraded states, and I need to define how can I transition to these states, how can I maintain these states. This can define like how do I do fault detection. A thing that is often done is like self-test mechanisms where like the software has certain consistency checks where it tries to detect like, do I actually get like completely nonsensical data? For example, like if a sensor is faulty, or even sometimes you even try like if the controller that you're running on is faulty, which is much harder to do. Another functionality that you often have is like if you have timing critical behavior, you typically have a watchdog of some sorts, right? That detects if you exceed your timing requirements, and that can either be a software or a hardware watchdog. And in many cases, you need the hardware because it's too hard to do for the software. You also look at the hardware-software interface. That's an important point here. You may optionally do what is called an ASIL decomposition, which means like if you're assigned a very high ASIL level, you can actually do this thing where you have like diverse implementations, and then the individual implementations have a lower ASIL level, but the overall composed system is able to meet the higher requirements. This sometimes is an more economic approach of the engineering. Ezra.
Is this all in parallel to like product feature and behavior implementation, or is it like in conjunction? It's all part of the same effort.
So it's usually done to some extent in parallel, right? Because like the development cycles are not that long, and you cannot really separate the phases. Then you just won't make it in time. So there's some overlap there, but it's. In the end, the goal of this phase is to meet the requirements from the technical safety concept, right? So as long as those people are not done, you're also not done, right? Yeah, that's how it works.
I was also wondering, so like this whole process, like new models of cars come
Yeah.
out like every year.
Yeah.
So this for every model of car.
Yes.
This
Yes.
whole process.
Yes, this whole thing. Which is why typically you don't rebuild the systems for every model of car, but you have like a platform that then is reused in different models, right? But and then you try to keep the commonalities as high as possible, right? Because if they are too different, then it doesn't work anymore, and you have to do all of this work again.
For the ASIL decomposition you just mentioned,
Yeah.
how does that contrast with the freedom of interference principle? Where like
Yeah.
an ASIL D system can't depend on an ASIL B system?
Right. This only works if you can show freedom from interference.
Okay.
So that is one of the prerequisites of doing this, and there's a whole section in the ISO how to do this. So it's it's pretty involved.
So it directly relates.
Yeah. These requirements then get reviewed extensively to again make sure that you have like this vertical verification and you didn't miss anything. Yes.
While we're on the topic of like this in the context of non-safety development,
Yeah.
do you have like some rough guess as to like relative ratio of time spent making sure that your music player works versus like making sure that your music player isn't blocking something more important? You know, I don't mean that specifically.
This is very hard to say. It's because like in the end, it's still the same software that you write that does both like the non-safety critical and the safety critical parts, and it's hard to separate, right? It's very clear and like very noticeable during development that if you work on a safety critical part, it's a bit more of a pain, right? You have a lot more stuff to do, a lot more steps to go through. But it's hard to give an exact number there, right? So it seems like, I mean, the whole, if you follow such a safety process, it's sort of pervasive, right? It has an impact on all the entire development that you do within the company, right? That is also what Jeff mentioned yesterday, where you have like this kind of safety culture, right? And that is always with you, right? And it's it's not easy to. I wouldn't be comfortable to give you a number there. Yeah. So these requirements will also be the basis for our software system tests in the end. Once we have the requirements, we move on to the architectural design, and now this should start looking a lot more familiar to what people are used to when just writing normal software. So the goal of the software design is, of course, like our system must verifiably fulfill the safety requirements. And the verifiably here is important. In particular, if you look at how automotive projects are typically structured, it's that the individual software systems are often implemented by different companies, right? And only in the very end they are integrated into like the same vehicle. So the verifiability is very crucial here to actually make sure that like the system actually fits into the vehicle and does all the things that it's supposed to do once it's put into the bigger context of the vehicle. So the goal of the architecture is to, Ezra?
Does that involve like designing the system so that you can intentionally trigger like faults to verify whether or not other surrounding systems handle that properly? Yes,
that is actually like the ISO particularly mentions it. They call it fault injection tests. That's a very vital part here. Yeah, you really should do that. Yeah. So the goal of the architecture is to break the system down into smaller components, right? Just as like if you've ever done software architecture, that's basically what it does. The standard here in particular requires us to describe both the static and the dynamic interactions. And the architects, the people that do this breakdown, typically also play a vital role in supporting the actual verification and implementation efforts. So typically these architects, that's senior engineers, in the company that have some experience already with how these projects work, and they sort of guide through this whole process, and they are often stewards for these safety efforts. The ISO actually describes what a good architecture should look like. So remember that the primary goal here is to avoid systematic faults, right? So if our design is too complex and we can't understand it anymore, it's very hard to be sure that there's no fault hiding underneath. So we really want designs that are comprehensible, that are simple, and that are verifiable. We want to break down into small self-contained pieces, right? We don't want an individual system to be so complex that we don't understand what it's doing anymore. And we also don't want the distinct systems to have interactions between each other that are so complex that we don't know what's going on anymore. We want clearly defined responsibilities, which again is also an enabler for the verifiability. We want to encapsulate critical data. And we want to make sure that the thing is maintainable, so that if it does come to changes, that we can actually make those changes without causing a big mess. And it points out many more measures to achieve this, like how you actually should structure it, that the components shouldn't get too big, the interfaces shouldn't get too complex, there should be loose coupling between them, and so on and so on. So the ISO points all of this out, and if you look at this, like this is just good software design, right? Like if you do software architecture, then like this is sensible, right? So this is actually nothing special here. It's just that the standard wants to make sure that what we know are the best practices, that you follow that, right? So that is all that they ask for us here. And then what you have in addition to what you would maybe have in an unregulated development project is that they also want you to produce the paperwork so that you can prove afterwards that you actually did follow these best practices, right? That's why, and at the end of this architecture phase, you also need to have a report where you basically convincingly argue that you did follow these things. So for this, the ISO actually also gives some hints at like what the form of the architecture should look like. So in particular, it says you should write documentation. This is actually required. This is not optional. And especially in higher ASIL levels, it's not just prose documentation, but they also want you to use semi-formal notation. So you all know like UML diagrams, architects like to draw boxes, right? But it might even go further where you actually, so there's, for example, SysML, where you can do system design, which then also allows you to perform like certain kinds of verification or simulation on your model. Or there's also like commercial products like MATLAB Simulink, where you can actually do really complex stuff in the model already. Yeah, as I said, the architecture needs to be verifiable so that you can test it in the end. And then there's some special concerns of the architectural design. So you want to partition the different software components according to their ASIL level. That goes back to this freedom from interference argument. If you have, you don't want a component which was developed with a lower level of rigor to be able to compromise the functionality that another component is responsible for. You want to analyze dependent failures. That's actually a vital step here. So like if one component fails, then it might produce faulty data, and that faulty data might lead to a failure in another component, and then you might have actually like a long chain throughout the whole car, and at the end of this you get a hazard. So there's a special analysis phase to rule this out. you want to actually be able to, in the end, have evidence, to have a convincing argument why your design is able to address the safety requirements that the technical safety concept was posing to you. There's a special analysis phase for resource usage and timing constraints, right? You want to be able that you actually don't overload your hardware and you're able to react to all of the situations in time. And then at the end, you actually do an extensive design verification phase, right? So like lots of things that you have to do. And yeah, as you can imagine, the architects are pretty busy here, right? So, and yeah, these are all things that the ISO like specifically calls out that you have to do. So that is where, yeah, a lot of the additional effort is spent here. Not going to talk about safety elements out of context for time reasons, but instead want to jump right into the implementation phase. So this is now where we actually start to write code, right? All of this so far was just conceptual things. Now we actually start to write software. And in many cases, we don't actually write software, right? So if a lot of development in automotive is actually still done model-based, where in the architecture phase, I have such a sophisticated model like MATLAB Simulink, and then I have a code generator that is actually able to generate the code from this, and then there's no implementation. This approach is getting less and less popular as complexity increases, because those systems have their limits, right? It's very nice if I have like a comparatively small state machine-ish logic that I want to implement. But like once my state machine exceeds a certain size, it becomes so hard to reason about that it's actually worth jumping to the code. But there's a trade-off here, right? So of course, the actual implementation relies heavily on the specification from earlier phases. We absolutely do not want people to just start writing code without being aware of like what the environment is in which this code will run and what the requirements from the other phases are. So the main goal of the implementation is consistency with what was determined in the earlier phases. Again, we want simple, readable, and comprehensible code so that we can actually be sure that what we have implemented is actually consistent with this. So that is the prime goal that we have here. We want the software to be robust to errors. We want it to be suitable for modification in case the requirements change, and we want it to be verifiable, right? So this shouldn't be a big surprise. So now the standard actually gives us some design principles that we can use during the implementation phase to achieve this. And this is one of my pet peeves. This is one of my least favorite parts of the standard.
This is 26.26.2?
Yeah. So this is the table 6 in part 6. So yeah, let's look at this. Single entry, single exit. You should not have more than one return statement in your function. Yeah. Let's move on. No dynamic objects. Okay, yeah, maybe in some systems. No uninitialized variables. I can get behind that.
What does that mean?
It doesn't.
You can't have an object on a stack.
It doesn't really say. I think they really mean you shouldn't put it on the heap and then like have dynamic heap allocation. I think that's what they mean, but they're not being very precise here, which is part of why I don't like this section.
Right.
Wait, so you don't use like dynamic, like any, like it's a vector, for example. That is just not.
That is the recommendation. Yeah, I will after we go through the list, I will actually tell you how to interpret the list. Okay.
So it's not like you have to use all of the kind of stack versions of this and that's it.
We'll get to that.
Okay.
So it says you shouldn't have global variables Yeah, I can get behind that. You shouldn't have variables of the same name, whatever that means. No pointers, I guess. No hidden data flow or control flow, which is often used as an argument for not having exceptions. And no recursion. This is mainly worrying about Stack Overflow. So this is pretty much like there's a table in the standard that pretty much lists these things. And the reason why I don't like this table is that people take these as like hard and fast rules. But that is not how these tables should be interpreted. Like there's a separate section in the standard that actually tells you how to interpret the table. And in the interest of time, what this table is trying to tell you is use coding guidelines. Right? That's what it boils down to. And there's a small section just below the table that actually like references MISRA C here. So yeah. You should be aware that there are certain dangerous constructs in your language that you might want to stay clear from. And the coding guidelines give you the framework in which you can do that. So let's actually look at what the requirements for the programming languages are, which, yeah, I guess like for this conference, that's probably a relevant part. So there is a section for this in the standard, but it's not very big. So what they say is they want an unambiguous and comprehensible definition, which is usually interpreted as you want a formal language spec. And you need a formal language spec anyway because your compiler that you use to build your software, you need to qualify this as well to make sure that there's no bug in your compiler that can compromise your software. And this is one of the reasons why in a regulated industry, you're really happy to have an ISO standard for your programming language. Zach.
Is C++ considered to have a comprehensible definition?
Yeah.
Okay.
Yeah.
I don't know if I believe that, but okay.
Yes.
Does this mean that like if you have a compiler that doesn't implement all of C++20, then you can't use your compiler for C++20?
No. Your compiler, if your compiler will come with a manual that actually says what it supports. And as long as you comply to what the manual asks of you, you're fine. Yeah, so if it asks like, I don't support modules, then just don't use modules, right? But the rest is still fine. Yeah. This also means no undefined behavior. Like they don't spell this out, but this is what is implied here and what the usual interpretation is. This can also, like, again, be interpreted as there should not be any footguns. So like no features which are easy to misuse and then like blow up your whole program. They ask you to, the program language support modularity, abstraction, and encapsulation. That makes sense. That is consistent with like the design principles that we saw before. And the last thing is they ask you to support structured programming. So like don't use assembly. Although they have a small note underneath that says like, yeah, you really have to use assembly like for small systems. You sort of can too, but we'd rather you don't.
I have a question. So does this say that you can't use a language that has undefined behavior, or does it say you can use a language that has undefined behavior, but you must not have undefined behavior in your program?
That's the next point. What they say is like, these are the things that we want from the language, but if the language itself does not provide this, you shall be using a coding guideline that actually covers the defects of the language. That is the weasel wording that they use here, right? Because I mean, like this is an industry standard, right? Those people know what the tools are that are being used, and the tools that are being used is like C and C++ to a large extent, and C and C++ has all of these problems. So they want us to use then a coding guideline standard that tries to mitigate this to some extent. That being said, I mean, these standards develop over time, right? This is the practice today. It might be conceivable that in a future version of a standard, it actually says that for these reasons, like C++ is not suitable, and we don't consider just using a coding guideline sufficient mitigation, and we'd instead want you to do something stronger. So either have like a really strict analysis tool that is able to give you these guarantees, or use another language, right? That is what people are afraid of when they say like there's a big existential crisis for C++ coming because of this, right? Because that is not inconceivable that the standard might change in this way at some point in the future. So what do they mean by coding guidelines? So what they had in mind was MISRA C or MISRA C++, which is not surprising because the people that wrote this section of the standard are, to a large extent, the same people that are behind the MISRA efforts. But it gives some hints here. So they want us to subset the language to exclude the dangerous features, or the features not suitable for this kind of development. Coding guidelines try to enforce low complexity, so that, as we've seen, that was one of the design requirements, right? We don't want you to write like incomprehensible large functions and spaghetti code and stuff like this. Another point is enforcement of strong typing. Concurrency is one thing that is pointed out here. The current standards don't do a great job at talking about concurrency, but in MISRA C++, there's actually an effort that has been going on for a couple of years now to actually have a specific document that addresses the specific concerns of concurrency and parallelism. And so MISRA C++, that is the guideline here. That's the big one that has been around the longest, and that is the most established in the field here. So the goals of MISRA are to discourage the use of dangerous language features, to promote best practices, and to avoid undefined behavior. And dangerous here can also mean non-deterministic runtimes. That is why MISRA discourages, for example, the use of dynamic memory in contexts where that could be a problem. There's also a different kind of guidelines that is often used in the automotive industry, and that is guidelines for quality metrics. So this is things like you get like, for example, an upper limit of how many lines of code a function should have, or what the maximum cyclomatic complexity, McCabe complexity of a function should be. This is used a lot in the industry. People are not really happy with it because it's like these metrics are not reliable indicators for quality, and they actually sometimes make the code worse. But they do have some value in like they do catch like obviously bad code, and we don't have anything better, to be frank. Yeah, so there's actually an ongoing effort in MISRA to get a better standard for coding metrics, but it's really hard. So yeah, what I want to point out here is that the guidelines is not just the guidelines. The guidelines is just one part. Equally as important is the process that we use for enforcing them. Because like for every guideline that we have, well, almost every guideline, there are situations where you have legitimate reasons for not following the guidelines, right? And how do you deal with that? Or like some of the guidelines only make sense in certain contexts, in certain system environments, right? And how do you figure out which guidelines to use for your project? And there's a whole document, it's called MISRA compliance, that actually talks just about that. And that is actually publicly available. So if you're interested in this, I highly recommend taking a look at this. There was also a talk by Loic Joly at NDC TechTown last year, where he talked all about MISRA and like how this works. How do you actually, like what does it actually mean if a guideline says you cannot do this, right? How do you deal with this in practice? What do you do if you want to not follow a guideline and stuff like this? Importantly, following the guidelines does not guarantee the absence of bugs, right? This is just like a best effort. So the most important thing for software safety is the testing, right? This is what gets the job done in the end, right? You want to test, test, and test. And like for the ISO has like sections for all of the different phases, how you should do testing, what are the things that you should look at. They recommend like you can do pair programming and code reviews to make sure that like you verified basic assumptions. They want you to use static and dynamic code analysis. They want you to use semi-formal or even formal verification, especially at the higher ASIL levels. They want you to do requirements-based testing, right? So each safety requirements that is passed into the software development process, you need to have a test for this specific requirement, right? This is very important for the traceability to make sure that you didn't miss anything. They want you to do the fault injection tests, right? As I said before. They want you to do resource monitoring, right? So that at all times, even during the development, you are aware of like what your budget are and if the software that you're writing is actually able to run within the constraints that the system has. And lots more, right? This is just like a small selection, and they give like detailed guidance of like what is important at each of the phases of the verification. Let's quickly also go over the testing methodologies that they mentioned. So they want you to analyze the boundary conditions, right? This like if you read the literature on safety, you probably know this, right? If there's an interesting boundary condition, this is probably a condition that you want to include in the test because that's where the interesting stuff happens. They also want you to analyze the equivalence classes, so that is sort of like the space between the boundary condition, right? If you have like 100 different checks, but they all fall within the same equivalence class, then it's not that useful, right? You want to make sure that you have all of the different equivalence classes covered and then the boundary conditions between them. They want you to analyze functional dependencies. And they have a whole section on like different kinds of coverage metrics that you want to use. There was actually a talk by my colleague Jürgen Kowalczyk at ACCU this year, where he talked a lot about like a specific metric that is very prominent in automotive, but not well known outside of it, is MCDC coverage. And he actually gave a talk like what this metric is and how you can check it. And in particular, he was writing on a patch for GCC to measure this metric with GCC, because it is actually quite hard to do this without commercial tools. You should really test on actual target hardware. And again, this is part of the safety culture. Your testing efforts should be continuously monitored. You really should have an eye on this. And in the end, there needs to be an approved report that actually verifies that you did do the testing, so that you cannot just skip it. All right. So as you have seen, like this is a lot of stuff, right? This is a lot of effort that is spent here, and a lot of different phases that we have to go to. A lot of people will be very busy with writing all of this, going through all of these analyses, writing all of these reports. So why do we do all this? Because it works, right? The standard reflects what the industry has been doing, like over the years, how they evolved their processes to arrive at a point where they are sufficiently sure that they have something that works. I think it's rather effective at catching issues and making sure that the products that fall out of this are actually safe. You could argue whether they are really efficient. So maybe some of those phases are overkill in some cases, but I mean, better be safe than sorry, right? So, and all of this like really has been proven in the industry. Like this was not just somebody like in their ivory tower writing this document. Like this is really industry experience that drives this. So yeah, really quick, safety is much more than a programming language. Lots of processes involved here. Most of the outcomes of those practices is actually not software, but lots of auxiliary products. But if you actually look at like the software developments, like the best practices that we saw there for the architecture and for the implementation, that is all stuff that should be familiar, right? That this is like what we understand when we say like we want to write quality software, right? So there's actually no magic here going on. And then, yeah, it's very important that you create an environment, this safety culture, where those practices are actually followed through, and you stick to these best practices and don't take shortcuts. Thank you. Zach, yeah.
Is fuzzing a testing technique that's used?
So the standard, if I remember correctly, does not mention fuzzing specifically, but they do have this blanket wording that says you should use the state-of-the-art methodologies for software development. And under that concern, I think like fuzzing is something that you definitely want to do. I think the security people are much more aware of fuzzing as a technique than the safety people. Yeah. Okay, so I'm getting the signal that we're on time. So yeah, thanks again.